All right, so before we move on from this example 13.1 completely, I think that we could probably all agree that the most confusing or the most difficult part of this problem was converting from this dot convention with mutual inductance to these two loops that we can solve very easily using mesh analysis. So what I want to do is I just want to take this extra page that I set aside to reanalyze the dot convention part of this circuit. So let's just take this and copy it. I guess what I can do is, I know there's an option to take a screenshot. There we go. Yeah, just like that. Okay, so copy, and then on this page we'll just drop it down. So let's just go through the exercise of transferring this over to the basically getting the dots and the mutual inductance out of the system so that we can solve this basic two-loop mesh analysis, okay? So what we have to take into account are where the dots are with respect to these inductors, and then we have to take into account this mutual inductance, okay? And so basically what we're saying, let's go back and look at what we did already. What we're saying is that this current I1 that flows through L1, that current is going to induce some current to flow in this other loop because these two coils are magnetically coupled, right? That's what the mutual inductance tells us, that these are coupled coils, and the dots tell us something about the orientation of these coils. And so we need to pay attention to this part of the circuit right here, basically. And so what we did was we basically said, okay, so from the dot convention, I know this. Let me grab this and copy it for us. From the dot convention, let's just shrink this. I know that positive current into the dotted terminal of one coil, hence this current, right, I1, is flowing into this dotted terminal of the first coil, is going to force a positive current out of the dotted terminal of the other coil. So pay no mind to I2 right now. We don't care about I2. I2 is the current that's flowing in this loop independent of the coupling, okay? So I2 does not matter here. Don't look at the direction of this at all. All we care about is the fact that if I know I have a current I1 flowing into the dot here, that means I'm forcing some kind of a current out of the dot on the other side. Okay, that's what the dot convention tells us. And so what the value of that current is depends on the current that induced it, right, I1, and the magnetizing, sorry, not the magnetizing, but the mutual inductance, okay? And so when we look at this voltage source that we created, we know Ohm's law tells us that V is equal to I times R, or for AC, it's I times Z, right? A current multiplied by an impedance gives us a voltage. And so we can represent this induction, this magnetic coupling that's happening in our circuit with a dependent voltage source that depends on the mutual inductance and the current that induced this voltage, okay? So the current that induced this voltage on this side of the circuit is I1, right? Because I1 is what's flowing through L1, and that is what induces a current in the other side of the circuit. And that current is going to be produced by this dependent source that we're modeling here, which is an impedance based on the mutual inductance and the current that induced this voltage, okay? And so the way that we orient this, right, because this one's upside down, this one's right side up, you're probably like, how the heck does that happen? That is depending solely on the dot convention, okay? So again, let's come back to the dot convention. I have a current I1 flowing into the dotted terminal here. That means I'm going to push a current out of the dotted terminal on the other coil. That's what this dot convention statement says. Positive current into the dotted terminal of one forces positive current out of the dotted terminal of the other. Okay, so that current is going to get forced out of that dot. That is the induced current. And now, so I need to basically place a dependent voltage source in my circuit here, somewhere in the circuit, that's going to force a current in that direction. Again, completely independent of I2. Do not look at I2. I need to force a current in this direction. How do I force a current in that direction? Well, the only way I can force a current in that direction is if I place a voltage source in my circuit that has the plus here and the minus here, because that's going to force current to flow out of that voltage source into whatever load it's trying to drive and back, okay? So that is the reason why that voltage source is oriented as such. If we look at the other side, now we look at this voltage source, this dependent source that we drew. Again, we're always going to know that we have a voltage source that we need to place into our other loop based on this magnetic, or this mutual inductance here, the magnetic coupling. And we know that on this side, this voltage is induced by the current that's flowing in the other side, I2. So now we look at I2, and we don't look at I1. We just look at I2. We see that I2, completely independent of this current that I drew, I2 happens to flow out of the dot, okay? That means that I need to assume that a voltage source is created on this side, which will force a current into the dot, completely independent of I1, okay? This has nothing to do with it right now. This is just the induced current from I2. And so the only way that I can do that is if I place a voltage source that has this orientation, because current's going to flow out of the positive terminal around the circuit, and then it will flow into the dotted terminal, and that is consistent with the dot convention, which is why we placed this orientation on the voltage source. And in both cases, the voltage is equal to the mutual inductance, or the impedance of the mutual inductance, multiplied by the current that induced the voltage. So again, on the left-hand side, I2 is the current inducing a voltage here. On the right-hand side, I1 is the current that's inducing a voltage here. Okay? So I'm going to just go ahead and wrap up this video. I guess I never even came over here, so that was kind of pointless. I wanted to basically redo the exercise, but I kind of did it here. So again, you know, I guess one more time, just for to say, you can't say I wasn't thorough. Of course, this is minus J4, this is J5, and then I know I'm going to have a voltage source here. Again, we look at I2 for this one. We're looking at I2. I2 flows out of the dot, which means I need to force a current into the dot here. So if I want to force a current into the dot there, that means it's going to flow in this direction. And the only way to get current to flow in that direction is to have an induced voltage polarity that looks like this. And it's the current that induced that voltage multiplied by the impedance of the mutual inductance. Okay, so that's that loop. One more time for the other side. I've got J6 here. I've got 12 ohms here. And then I'm going to have an induced voltage source. This time we're looking at I1, so it's going to be I1 times J3. We already know the size, but we don't know the polarity, so let's look at the polarity. It is current flowing into I1 forces a current out of the dot of current flowing into the dot here, which is I1, forces a current out of the dot here. In order to force a current out of the dot, which is in this direction in this circuit, I need the polarity to be plus to minus like this. So this is how I draw my polarity, and I'm ready to solve this problem. Of course, I would put I1 here, I'd put I2 here. And so again, I just wanted to run through the dot convention because I know that's the more difficult part. Once you get it to this stage, it's really not difficult. In the next video, next couple videos, I'm going to solve another example from the other textbook. It's going to take us from the component values over to the impedance phasor domain. And then we'll go basically through a similar process where we solve using mesh analysis. We look at the dot convention and we transform the circuit to something that we can solve. We go and carry out the algebra, etc. So we'll get some more practice with this, but I just wanted to run through it one more time because I know that this is not super intuitive at first. So if you have questions, let me know. Gonna wrap this video up here and we'll see you guys for the next example problem.